Hello, and thanks for joining this World Water Day Groundwater Chat with the Jameel Water and Food Systems Lab, or J-WAFS. We are a program that funds water and food-related research at MIT. My name is Carolyn Blaze, and I am the Communications and Program Manager at J-WAFS. March 22nd marks World Water Day, an annual United Nations observance that celebrates water and raises awareness of the billions of people living without access to safe water. This year's theme is groundwater. Out of sight, under our feet, groundwater is a hidden treasure that enriches our lives. But what is groundwater, and how exactly is it used to enrich our lives? Is all groundwater safe? And where on earth is it found? We'll explore these questions and more in a discussion with J-WAFS Director John H. Lienhard and J-WAFS Research Manager for Climate and Food Systems, Greg Sixt. Welcome, John and Greg. Would you like to take a moment to introduce yourselves?
Sure. I'm John Lienhard. I'm a professor at MIT. I'm in the Department of Mechanical Engineering, where I work on water supply, desalination, and heat and fluid flow. I'm also the director of J-WAFS, the Abdul Latif Jameel Water and Food Systems Lab, which is an MIT-wide initiative in water and food research. We cover all departments. We funded essentially all units at MIT.
And I'm Greg Sixt. I'm the director for the Food and Climate Systems Transformation Alliance, J-WAFS-led global initiative. And I'm also the research manager for Food and Climate Systems at J-WAFS. My area of expertise is in groundwater governance and agricultural knowledge and innovation systems.
Okay, great. Well, thank you both for joining us, and let's just jump right into it. So, Greg, I'm guessing groundwater is exactly what it says it is, water found in the ground. Is the definition as simple as that?
It's kind of as simple as that. So groundwater and aquifers are synonymous. That you might have heard the term aquifer. I think some people might visualize groundwater as like an underground lake, just under there with, water, surface water, but it's not. It's, what groundwater or what aquifers are is porous, rock or soil or sand in which the water is kind of embedded in between the particles, and it's accessible, by drilling down to it. It can be anywhere from, right at the surface all the way down to hundreds or, over thousands of feet.
Okay. And John, maybe you can tell us, why is groundwater important?
Groundwater is important in part because it's one of the major water supplies of the world. Fresh water, from rainfall lands on the surface in precipitation, but where the ground, as Greg mentioned, is porous or where there are fissures of one sort or another, precipitation finds its way underground. And it travels through porous layers in the ground. It collects in them to form aquifers. And humans have figured out how to extract that water, either by digging a well or drilling a well, and pumping water up where they can. In some cases, we're lucky and groundwater just comes naturally to the surface as an artesian spring. But quite often it takes a little more effort to get down there and get it out of the ground. But it's used for household supplies, for municipal supplies, for irrigation and farming. And it's used worldwide.
Okay. And that brings me to my next question. Is most of this water that's under the ground drinkable, or is it brackish? And how does it compare to, say, seawater?
The water in the ground in some cases is fresh and can be pumped up and used. In some cases, it has a certain amount of what's called hardness. The stuff that kind of scales up your pipes and may require some softening. And in some cases, the water contains significant levels of salt, dissolved salts, which is not just sodium chloride, table salt, but it might be calcium and carbonate, magnesium and sulfate and various other things that come from the rocks in the ground. As it turns out, if you look at sort of annual water consumption in the U.S., the amount of brackish groundwater in the U.S. is maybe 35 times larger by some estimates. So there are significant amounts of groundwater that are brackish. The United States Geological Survey has recently updated its atlas of groundwater. It has samples from more than 100,000 wells. And from our analysis, on the order of 20 or 30,000 of those wells are quite brackish. And, those are just the things that have been sampled to give you some idea.
And to build off of what John was saying, another issue with groundwater is pollution from surface, right? So especially under agricultural areas, you've got an increasing problem worldwide is nitrate concentrations, of nitrate, which can have impacts, especially to children and babies if the water is drank. Much of the land underlying major agricultural production areas is polluted in some level with nitrate. But another kind of key point here is that about 2 billion people in the world rely on aquifers as their primary water source. So it is a fundamentally important source of water, and it's one that we're kind of starting to understand. We're only starting to recently understand better. The technology to really start to monitor it and model it is relatively new when you look at it compared to things like surface water or other sort of natural resources that we use.
You had asked me about the difference between groundwater, brackish groundwater, and seawater. That's an important difference in the sense that seawater is much, much saltier than most brackish groundwater, and saltier in the sense that it may contain 10 times the number of dissolved ions, 30 times the number of dissolved ions. And so when you think about, treating or desalinating seawater, you're looking at a process that takes considerably more effort or specifically more energy than desalinating brackish groundwater because you don't have as much content to take out of the water. So that's an essential thing that makes brackish groundwater in some sense a more attractive resource than seawater.
That does bring me to another question, John, for you about, the technology that you use. If you can touch on that a little bit, I know you said it takes a lot less energy to treat the brackish water as opposed to the seawater. Can you tell us a little bit about the method you have found for treating that kind of brackish groundwater?
Sure, happy to. The world standard, the most common technology for desalinating seawater is a process called reverse osmosis. And what reverse osmosis is essentially is a semi-permeable membrane where you pressurize seawater on one side of this membrane. The membrane only lets water through. It won't let salt ions through. So the water passes through to the lower pressure side as essentially pure water. Now, the thing is, with seawater, because you have so many ions, the pressures have to be much higher, about 70 atmospheres. It's a typical working pressure for a seawater RO system. For brackish groundwater, you can use RO, and depending on the amount of salt present, you may only need a few atmospheres, maybe only 10 atmospheres, maybe 5 atmospheres of hydraulic pressure to desalinate the groundwater. But there are other ways to do it because the concentrations of ions are lower. Another common technique is something called electrodialysis, which uses electric fields and, again, semi-permeable membranes to allow some ions to move through the membrane and others to stay behind. And so you can purify water by blocking all the ions from going through, or you can select which ions you'd like to let through if you choose to, using other kinds of membranes. And so electrodialysis is typical for groundwater treatment as well. I should add, salts per se are not the only thing that we worry about in groundwater. And, depending on what kind of rock structures are beneath the community in question, you might have uranium in water. You might have arsenic in water. And the treatments for those ions may often go in another direction, ion exchange resins or some other technology. I should emphasize that arsenic in groundwater is a major health issue in some parts of the world, including in some parts of the U.S.
And to build off that as well, in some places, John mentioned uranium in groundwater. In some places, the point I made about fertilizer nitrates infiltrating groundwater, what they've actually found, like in places in like parts of Nebraska, for instance, in a city of about 40,000 people called Hastings, Nebraska, where they've actually found that the nitrates have mobilized uranium that was, that's natural to the soil, the geology has mobilized that and actually they were, first treating one problem, the nitrates, and then they found out that over time it was actually nitrates were increasing the uranium challenges in the water. So, human activity has a real role to play in the quality of our groundwater as well as natural systems.
Greg, can you tell us, is groundwater found all over the earth? And I know you have done some research around groundwater governance. Are there parts of the world where people are perhaps fighting over the groundwater or, maybe there's not enough to go around?
So groundwater is found on all the continents in the world. And it varies considerably by location, right? So in some areas, you may have groundwater that the geology is more sand-like. The groundwater is called recharge. So as it rains, it's basically as long as you are withdrawing or abstracting less than is infiltrating on a yearly basis, you're either, increasing your groundwater levels or you're maintaining it. So in some places, the soil is sandy, and it recharges quite fast. In other areas, the opposite extreme of that is what's called fossil groundwater, where it actually, it's from thousands of years ago, tons of thousands of years ago, and it may be trapped below a rock layer or a clay layer and doesn't really recharge. And so when you use that fossil water, you're actually mining the groundwater. Once it's gone, it's gone. In other areas, we are withdrawing it so fast that the ground's actually sinking. And once the aquifers collapse, there's not an opportunity for those to recharge. In other areas, if there's coastal aquifers with sea level rise or with overpumping of groundwater, you start to get sea level infiltration into the groundwater. In terms of governance, there's kind of two key terms that are really important. One is common pool resource. And so virtually all types of water resources are common pool resources or CPRs, and groundwater is one of those. And what a common pool resource means that the resource base is sufficiently large to make it difficult to exclude users, and each individual's use reduces benefits to users who share the resource. So other examples of common pool resources are forests, fisheries, like these are things that are really difficult to govern because the logical move for an individual is to use as much as they need, or sometimes even to use more than they need. But collectively, that depletes the resource. And the other is social ecological system. And so a social ecological system is one that is connected and impacted by one or more social systems, so economic systems, drinking water systems, for example. And it's a subset of it's that interplay between human relationships are deeply involved with the biological units, the non-human biological units, and the biophysical conditions. So to my point earlier, where human behavior has a dramatic impact on the water, the groundwater we rely on. In terms of governance, the common pool resource element is the key one. There are different ways in which water is governed, groundwater is governed. I tend to have more knowledge on the U.S. on this, but there's kind of two fundamental principles to groundwater governance. One is the important distinction between a property right and water for the public interest or public welfare. And the other, and this has a really major impact on management options. So if groundwater is considered a property right in the U.S., if any kind of state agency that tries to limit withdrawals, that's considered a taking of the private property under the U.S. Constitution. So that makes it much more difficult to manage. So in a place like Texas or Kansas, groundwater is a property right, which limits the ability of the state to be able to control resources. In a place like Nebraska, the groundwater is owned by the state for the benefit of the people. And that distinction has a real impact on how you can manage it. And the other fundamental principle of groundwater governance is allocation rules. So one is, and these are related. One is the rule of capture, which means that landowners own all the water that underlies their land and can pump water without limitation. And that's got real implications because aquifers or groundwater doesn't abide by property boundaries, right? I mean, if I'm over pumping on my land, it's impacting my neighbor's availability. The other is reasonable use doctrine, which allows a landowner to use the groundwater underlying their land, provided it's for a reasonable purpose and used on that land. The other is determines kind of use based on the amount of land a person owns. And the other is prior appropriation, which means that first in time, first in right principle. So if you owned your land first, or you own your water rights, you have senior water rights. And that's actually, you see that issue in places like California, where during drought, you might hear that, junior water rights users are losing access to their water. So these are kind of the key principles. I might have gone down a bit of a rabbit hole here, but they're kind of important things to understand if you're talking about groundwater governance. That property principle is really key.
That's super interesting. I had no idea of that. It varies from state to state.
Yeah, groundwater governance in the U.S. is a state-by-state issue. There isn't really federal oversight of groundwater, except for where there's interstate issues. Also, you've got groundwater that spans international boundaries. Even in many fully developed countries, we aren't great at managing groundwater. And, so what does that mean for places that don't have as strong of institutions? How do you tell a growing population to use less when it's a poor region that is just trying to feed itself? And this is that social ecological systems, right? The interconnectivity of our ecological systems and social behaviors. And it's a really difficult thing we're going to have to deal with over the coming decades.
And the ownership of water and the access to water, they're certainly tied up in economics. In California, water rights are becoming more valuable. And there are actually investment funds that have been set up to purchase and hold water rights because they're perceived as becoming increasingly scarce. And so, in fact, you see some major endowments of big institutions purchasing into funds that are buying water rights on the hope that those investments will become more valuable as water becomes more scarce. Think a little bit about what that means. It's not like we're talking about handbags or tulip bulbs becoming scarce and expensive. We're talking about something that is a human right becoming scarce and expensive. And so there will certainly be significant social tensions arising if trends like this continue in the direction they're headed.
So we've already touched on some of this, but I guess what are some of the biggest threats facing groundwater? Is it climate change? Is it pollution?
I think the answer is all of the above. Climate change is drying out areas, which is, increasing the need to pump. Population demands are increasing demand for water. The population growth is increasing demand for water. Sea level rise, as I mentioned, is inundating coastal aquifers. And I think we've got something along the lines of about a dozen of the world's aquifers, the major aquifers in the world, are depleted to the point where regional water availability is threatened. I think one of the other challenges too, where, so I kind of view groundwater as the other shoe that, to drop. There's a lot of focus on surface water. It's easy to see. It's easy to see when surface water is polluted. It also can be polluted relatively quickly. The change is quicker. We often forget about what's under our feet, and the changes that occur in groundwater occur over the course of decades. So one of the challenges is, if you discover pollution, a source of pollution in your groundwater, depending on the geology, that could be, for instance, over-fertilization that occurred 30, 40, 50 years ago. And so when you're asking farmers or when you're asking communities to make changes to restore that groundwater, you're asking those farmers to make changes that they will likely not see the results of in their lifetime. Right. So if you're changing farming practices, in fact, you may actually see pollution levels increase after you implement some control measures, because there could be a plume of pollution working its way down through the soil before it gets to the groundwater. So these are one of the challenges, some of the challenges that make governing groundwater really difficult.
Well, one of the biggest threats is that groundwater is simply being overdrafted all over the world. It's become more and more clear as we've developed better techniques for measuring the amounts of groundwater. And you think about that for a minute. The groundwater is underground. You don't easily see where it is or how much is in the ground. But there's been some great work done with satellite sensing to actually detect where groundwater has been falling and the rates of use. And recent work in the last 5 years or so has shown that most of the world's major aquifers are overexploited and the water tables are dropping. In some places this has been known without the need for satellite studies. For example, if you go to the Central Valley in California, where groundwater is freely pumped, typically, as Greg was explaining, by senior water rights holders, and they pump as much as they want in order to grow things in what is otherwise a fairly dry area of the Central Valley. And the result has been that the surface ground level has subsided. And there are areas in the Central Valley where the land is now more than 50 feet below where it was 100 years ago because of the overexploitation of groundwater. One of the things that's of great concern there is that as you allow those soils to compact, it's not obvious that putting water back in will allow the soil to again absorb as much moisture as it used to, because it really does become compressed and you lose the porosity between, if you like, particles of soil. But more broadly, there just doesn't seem to be the prospect that water is going to be replenished while current trends of use continue and while current change in the climate system continues as it has been. So what's really needed in those cases, in part, is to rethink the model for how groundwater is used, to rethink, as Greg outlined, the processes through which groundwater is governed, and, of course, very importantly, to have a more integrated water management strategy, management across the state, management across the region if necessary, and management that is based on current trends and conditions, not on structures and realities that were present in the late 19th century.
We've certainly highlighted the severity of the problem. Just to wrap up, and is there anything we can say on a hopeful note?
Well, the good news is that there are many different ways to practice agriculture. And there are many, technologies or approaches, perhaps not even technologies, practices available that can help to reduce the intensity of water use in farming. A notable example is drip irrigation, where water is essentially dripped around the roots of the plants instead of being sprayed all over the place. There are, practices such as growing cover crops that help keep moisture in the ground. Any number of things can be done differently to help back off the intensity of water in agriculture. There, of course, are efficiencies to be had in urban water use as well. Now, agriculture is probably 70 or 80% of the world's water consumption. It is by far the biggest actor. But cities can become much more water efficient through the appliances they use, the fixtures they use, through the reuse of water, through landscaping choices and other things. Very significant efficiencies can be obtained. Industrial use of water generally is becoming more efficient over time because water is a scarce resource and your business is more effective if you use less of a valuable resource. So I think that there are a number of things that can be improved and will be improved as a matter of necessity, if nothing else. There are high-tech solutions for sure, precision agriculture, where people use all sorts of remote sensing data to figure out exactly how much fertilizer to put down so you don't wreck the groundwater. Figure out exactly how much water this part of the field needs as opposed to this part of the field. That's very advanced stuff. That's not available to smallholder farmers in particular, but it is an example of sort of the high-tech end of what people can do. And in other cases, MIT, through the Poverty Action Lab and a project that J-WAFS was involved in as well, have looked at giving farmers in India, say in Gujarat, conservation credits, essentially doing some metering and paying them for using less water. And the studies they've done suggest that techniques like that can be helpful.
Yeah, and there are absolutely areas where you can look to for hope. I mean, one is actually we talked about California and some of the challenges they're facing. California recently passed the Sustainable Groundwater Management Act, or SGMA. If that's fully implemented and effectively implemented, that really could make a big difference in how they manage their groundwater. And also in that SGMA law from California, you actually see a lot of elements from Nebraska's Natural Resource District system and how they manage their groundwater. And Nebraska is actually a kind of a pretty good model of how you develop empowered local governance institutions with the ability to implement control measures with more of a kind of a systems approach, and that makes it somewhat adaptable. And the other area of hope is that simple ancient technologies such as water harvesting, which go back thousands of years, can actually be reintegrated into modern production systems. So once you start to have this systems approach, you can start to see how the pieces relate. And so there is a move towards that, and that does give hope because the trade-offs are important to analyze, and these approaches provide some means to do that. So it is easy to focus on the challenges we face and how that could keep you up at night. And we are facing a pretty big uphill battle on a number of fronts, and groundwater being one of them. But there are kind of silver linings, or there's at least glimmers of hope, and there are examples we can look to on how to improve things. And so I think it's an exciting time to be in water governance and water management, and we need good people to work on this.
Well, thank you both. That was a super informative, great discussion. I think we've learned a lot about this precious resource. And just thank you both. Happy World Water Day. Anything else to add?
No, I just thank you, Carolyn, for the opportunity to talk about these issues, which are of critical importance to everyone. And I think it's very important for folks to think a little bit about how much they rely on water and access to water, and how they're going to ensure that for the future here on World Water Day.
I think it was Benjamin Franklin who said, when the well is dry, we know the worth of water.
That's right.
That's a good one. Thanks.